We're going to work a path planning example in robotics. I have the example set up here. I'm going to do a screen share. Okay, so presented here with this robot, it looks like it's a 3DOF robot. It has theta 1, D2, D3. We're given the following manipulator with frames, D and H table, inverse kinematic solution given here. And we're asked to define a continuous second order smooth path between point 1 and 2 with velocities defined here 0, or if you want to be a little more advanced, velocities is defined here over the time step from 0 to 1 second. And we're asked to find the joint variable equations for the joint variables that are functions of time. So we need an equation for theta 1, describe that path as a function of time from T1 to T2. We need an equation for D2 similarly, and we need another equation for D3. That's what we have to get. And we want to write these equations in this case as cubic splines. I think it said cubic splines. Where did it say cubic splines? Yeah, cubic splines. Now, the first step is, so we jump and look at our cubic spline. We had that from path planning. So scroll down real quick. We can get the equation for cubic spline and have it right here. Grab it, take it with us. There's our equation for the cubic spline. And that gives us the coefficients of a description for our Q as a function of time. So from that, I get Q is A0 plus A1T plus A2T squared plus A3T cubed. And that's the function we're looking for each of these. I've got to solve it for theta 1, D2, and D3. I'm given the robot positions at time 1 and 2 in tool space. So I've got to go from tool space first. My first job is to go from tool space to joint space. So let's do that for our 3 conditions. The first one I have here is we'll start with D3. So I need D3 at time, I guess I'll put it up here as a superscript. At time 1, D3 will be is plus or minus the square root of x squared plus y squared. So at time 1, x is 200 squared, y is 0. So D3 is 200. I'm taking the positive solution. I go to theta 1. Theta 1 is the inverse tangent, a tan 2, if you will, of y over this x over d3y, negative y over d3. Let's see, x is 200 over d3, so that's 1 over y is 0. So the inverse tangent of that's infinity. So I know that happens at 90 degrees. So theta 1 is 90 degrees. And then finally, D2 is z minus, and this is at time 1. D2 at time 1 is z minus D1. So that's 200 minus D1. D1 is right here. So that's 100. So that's at t equals, that's at T1. At T2, I have to do the same thing. So my D3 at time 2 would be x squared is 0 plus 200 squared square root, which will again be 200. I'm going to take the positive solution, so I'll choose 200 positive. I need to get my theta 1 at time 2. That's going to be the inverse tangent again of x over d. So my x is 0. My y is 200 over d3, which is 200. So that's 1. So that's the inverse tangent of 0, which is 0. No. So 0 over negative 1. X is 0. Y is 0. Run is negative 1. So that's 180. That is 180. since I had a negative here. And then finally, I think I've got that correctly. So my rise is 0, my run is -1. I'm calling that negative 180 or positive 180. Finally, my D2 is Z minus D1. So time 2, my Z is 500 minus D1, which is 100. So that's 400. Okay. So now I've got my joint parameters. These are effective. These are the Qs. Notice I also need the Q. So, and I've got them at time 0 and at time 1, or T1 and T2 in this case is what I'm calling them. We also need the Q dots. So I've given this problem, sort of a intermediate and advanced. The intermediate case, V1, which would be the, V1 as a vector just says it's just zeros. So it'd be 0, 0, 0. And I could go to my Jacobian here. And when I solve that, that's going to give me D3 dot equals theta 1 dot equals D2 dot at 0. And the same with B2 equals 0, 0, 0. And that's going to give me a D3 dot equals theta 1 dot equals D2 dot, again, as 0. And then if I have non-zero velocities, that's for the zero velocity case. If I have the non-zero velocities, if V1 is 0, 50, and 0, then I have to put that into my equation for my velocity. So I've got the Jacobian. My relationship is the velocity equals the Jacobian times my Q dots, which in this case would be, well, they got to be in order. So it's going to be theta 1 dot, D2 dot, and theta 3 dot. In the first case, well, let me put it like this. Then Q dot is the inverse of J times E. So that means I've got to solve for my Q dot as the inverse of J. So I'm going to plug it in here. I've got cosine theta 1 times D3. Well, cosine theta 1 is 0 because it's cosine of 90. So that's 0. Sine theta 1 is 1 times D. So that's 200 and 0. Second row is 0, 0, 1. And third one. And by the way, while I'm doing this, I'm going to start MATLAB. I'll need some way to take the inverse of this matrix. I'm going to throw that up over here. The third column is going to be the sine of theta 1, which is 1. Cosine of theta 1 is 0. And then 0. So I've got to take the inverse of that guy times my V, which is 0, 50, and 0. My MATLAB is still, and that'll give me my Q dots, or my D, or excuse me, my theta 1 dot, D2 dot, and D3 dot. And I've got to do the same thing over here. So here it's going to be Q dot equals, I'll put in these values. So now theta 1 is 180. So I'm going to have -1 times D3, or -200, 0, 0, 0, 0, 1. And then sine of 180 is 0. Cosine of 180 is -1 times a negative. So it's +1, 0. Inverse times my V, which is 50, 0, 0. So again, my theta 1 dot, D2 dot, and D3 dot equals, okay, so we calculate those. Got MATLAB open here. So we're going to put it right in here. So I'm going to let my J equal, in the first case, it's going to equal the matrix 0, first row, space 0. 0, space 0, space 1. Second row, 200 space 0 space 0. Third row is 0, 1, 0. And I'm going to take the inverse of that, of J, times my right-hand side, which is an array, which is going to be 0, colon 50, or semicolon 0. And I'm using semicolons to make it a column. And that's my answer. So I get 0.25, 0, 0. Okay. And now I have to do the same thing for my second time step. So now I've got my J matrix is negative 200, 0, 0. Second row is 0, 0, 1. Third row is 0, 1, 0. Look at that. Again, I'm going to multiply that, times my V, which is now 50, 0, 0. Yeah, I forgot the semicolon. So this time I'm going to use a transpose. Guess I'm doing both options. I get negative 0.25. Okay, well, I guess I'm just going there. Okay, so negative 0.25, 0. Okay, seems a lot, but I'm just going to stick with this, push on through. Okay, so now I've got my values. Now I'm ready to, I've got my joint variables at the beginning and end conditions. So all I've done so far is map from joint tool space to joint space. That job is done. Now I've got to find my trajectory. So we're going to start with, we'll start with theta 1, okay? So my theta 1 equation, I need my coefficients. So I'm going to get an A0, A1, A2, and A3. It's going to equal my matrix. My matrix I have to evaluate at T0 and T1, which here we're calling T1 and T2, which are 0 and 1. That make it easy. So I get 1, 0, 0, 0. I'm putting in the values of T1 equals 0, T0 equal 0 in this equation. 0, 1, 2 times 0, which is 0, and then 0. Third equation is 1. T1 is 1. T1 squared is also 1. Finally 1. And fourth equation is 0, 1, 2, and 3. And I multiply that by my Q0, which is theta 1 here, which is 90. Q0 dot. So for the case where the velocities are 0, I would put in 0. When the velocities were non-zero, I had 0.25. Okay. So you can solve either one. I guess I'm going to start by solving for the 0 case, but you would plug in if you're solving it for the non-zero velocities, you plug in that value. Then I need Q at time 1. So theta 1 at time 1, which I'm calling T2, is 180. And then finally Q1 dot at time 2, which is 0 for the 0 case, or negative 0.25. Okay, so I'm going to go back to MATLAB and solve this guy. So my T matrix is going to be 1, 0, 0, 0. Next row is 0, 1, 0, 0. Third row is 1, 1, 1. Fourth row is 0, 1, 2, 3. So I get my T. See. And then I'm going to take the inverse of that. So I'm going to take the inverse of T, and I'm going to multiply it by my right-hand side, which is 90. I'm going to write it out as a row vector, and then I'm going to take the transpose. So 90, 0, 180, 0. And notice I'm leaving in degrees. By the way, I have to make this an array. I'm leaving in degrees, so that means my answers are in degrees. I always have to watch those, the units, and I got to take the transpose of that. So this is my coefficients. Oops. Look at that, 90, 0, 270, 180. Okay, so that means my equation for theta 1 is 90 plus 0 times t plus 270 times t squared minus 180 times t cubed. And that's for the velocity equals 0 case. And if I wanted the velocity to be the non-zero case, I would have put in 90, 0.25, negative 0.25. And I would have gotten that set of values. Okay. Small change, but there you have it. I can let's do a little screen grab here. So if you want to see it. Okay. So that was our theta 1. Maybe I could tuck this up here. All right. Well, I mean, we're on a roll. Now we've got to do, now we have D2. So we get our A0, A1, A2, A3. So we get this, oh, by the way, I forgot my inverse. We get this T matrix. It's the same time. It's the same T matrix. Here, I'm going to write it out. It's going to be the same. Same exact T matrix, 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, 1, 2, 3. Got to invert that. I'm going to call that my T matrix. This time I have to multiply it by my Q0, Q1, where Q is my D2. So at the initial state, D2 was 100. At the final state, it was 400. At the initial state, the D2 value was either 0 or 0. So I guess it's 0 in both cases. So I need that guy. So I come back up here. So I get 100 space 0 space 400 and 0. And that gives me 100, 900, and negative 600. So D2 is 100 plus 0 times t plus 900 times t squared minus 600 times t cubed. And then finally, I get my D3. And again, I need my coefficients, A0, A1, A2, A3, times this now, this matrix T squared. It's the same matrix, not squared, inverted, times my initial and final values for D. And initially it was 200, and it stayed at 200. Yep. So D3 stays at 200. Okay. And the velocities we saw for those were also 0. So I'm going to come over here to our matrix, or to our solution. So I need to make that guy 200. I need to make this guy 200. And that just gives me, it's just 200. It's always 200. It doesn't move. So that's 200, 0, 0, 0. Okay. There's a little bit in the Jacobian that I feel like I need to track down. But in terms of method, we're seeing the method work out here. So D3 is 200 plus just 0 times t plus 0 times t squared. Okay, now I have descriptions for my robot path from time 0 to time 1. I can sample at any time t. It satisfies those boundary conditions which were given in tool space, and that completes this problem.